Sorry to interrupt you. So can you please start the recording?
No, I did not get. What is that?
No, sir, it's okay. Someone has started the recording.
Yes, sir. Yes.
No, you want to record. I did not put in recording. Somebody is recording.
Yes, sir. Yes, sir. It is fine.
Please don't do that, right? I mean, nowadays it's okay. I forgot to record it.
Sir, you are muted.
Sir, you are muted.
Someone muted you.
Who is muting it?
Muted.
No, who muted?
Sir, make everyone participate, attendee, sir.
Yeah, I made it already.
No, sir. Everyone is a presenter right now. Like everyone has controls over muting and removing.
Really, that's right. Just hold on a minute.
Sir, you are muted.
Can you check it? Now, are you able to mute me or mute others, unmute others?
No, sir.
Yes, sir. Now we are attendees, sir.
Okay, right. Yes,
we
yesterday
can-
this was not the case, right? Can you hear me?
Yes, sir. We can.
Okay, right.
Yes.
Let's go. Let's go. Please play around, but don't play around, right? Let's be serious. So 2 hours. I will give a break in the middle. Please, I mean, don't play around, right? Because you may be playing, but disturbing all others. So my humble request, don't do that. Right. Okay. Now you go here. I have a fluorine, F2. Okay. Now you have a F2. Now the same way. What do you need to know that? You need to know the atomic number, and then know the number of electrons, and then fill it from the 1s, right? Though you are not showing the 1s MO here, but it's filled from here. Now at the end of the day, what we can do is that you can calculate your bond order, and you can predict whether this molecule or this system is paramagnetic or diamagnetic. Quite straightforward, right? I hope you follow that. Am I right?
Yes, sir.
Yes, right. Quite straightforward. What do you need? You know the atomic number, find out the number of electrons, and then start filling the number of electrons from the 1s MO. What do you need to follow? Of principle, Pauli exclusion principle, and the fundamental principles that you follow it. Right? Now, let me ask that. Let me ask you. Right now, I'm giving you a molecule that's B2. Okay. I'm giving you the molecule B2. Okay. B2. What is the atomic number for boron? Anybody? Unmute and tell quickly.
5.
5. Can you tell me that? Now you quickly do that. Quickly. We don't have much time. What should be the magnetic property of this molecule? That is the B2.
Paramagnetic.
Pardon?
Paramagnetic.
No, I could not hear. Can you repeat once again?
Sir, paramagnetic.
Paramagnetic. Right. How did you get paramagnetic?
So there are two unpaired electrons in the
Unpaired electron, right? Now you see here. I will show in a different way. I don't know how did you get your paramagnetic. Okay. Now what we have here is that a B2 molecule. Now I have a 2, 4, and 6. Okay. Totally 10 electrons. Am I right?
Yes, sir.
4 electron goes to the 1s orbital. Here I have a 2, 4, 6, and then 4 here, totally 10. For me, it is diamagnetic. I don't know how did you get the paramagnetic. Right? It's puzzling, right? I mean, is it really diamagnetic? Or I don't know. How did you get your paramagnetic?
It is.
No, I can't hear. I think my voice. Okay, right. Let me go here. I put a question here, right? Whether it's diamagnetic, according to what we have seen so far, you follow the Offer principle and Pauli exclusion principle. Everything you follow it, fill up this. 4 electron goes to the 1 SMOs, and then 4 electron goes to the 2 SMO. Remaining 2 you have, that goes to 2p orbital, that is your sigma, right? It goes here. Now, let me see here. I'm bringing a concept of orbital mixing. Right? Look at very carefully. Very carefully look at this one. What I'm going to talk about, teach you is that there's an orbital mixing. Here, according to whatever the electron that I filled, the order of electron filling, this should be a diamagnetic molecule. There is no doubt here, right? Now, here, look at here. What I have plotted here is atomic number. There's a first row diatomic, right? Atomic number. And here I have atomic orbital energy in kilojoule per mole. Okay. So this is for the 2s orbital, and the blue one is for the 2p orbital.
Sir, I have a doubt.
Yeah, let me finish it.
Order,
Just hold on, please. Let me finish it, and then you finish this, and then you ask. Right? Now, what you have is that I have a 2s orbital, atomic orbital energy is plotted against the atomic number. That is the first row diatom. And then the same way, I have a 2p. Now, what is that here is the energy gap between these two, right? Say, for example, the say boron here and here is 2 less with respect to compared to the energy gap between these two orbitals where you have a fluorine. So the energy gap between the 2s and 2p orbital of fluorine is higher with respect to, say, for example, boron and carbon and nitrogen. Now, the concept comes here, if the energy is very close to, similar to each other. Right? Yesterday I mentioned the symmetry and the energy. Now, here what we have, the energy between these two orbitals, 2s and 2p orbital of boron is close to each other. If that is the case, why can't these two MOs or why can't this atomic orbital mix together?
So sp mixing will be there.
Yes?
So sp mixing will be there.
Yeah, it's a mixing of your orbital. Now look at here. What I mean? The fundamental concept what I'm teaching is that the energy gap between your 2s and 2p is too small. So it can undergo mixing, what you call the orbital mixing. You can read it from the screen, right? So now, what is the implication of this orbital mixing? The order of the MOs changes. Say, for example, if there is a mixing, orbital mixing is happening, what happened? This is before mixing. There is no mixing here. If there is a mixing takes place, what happened? The order of the MO changes. Where we'll be able to see here. Now here you have your sigma G. There's a blue colored circle. That is now in the case of mixing, it rise to above your pi MOs. Right? This is basically due to the mixing. Why mixing comes into picture? Because of the energy difference between these two atomic orbitals is too low and it can undergo a mixing. So the order changes. Same symmetry and similar energy, why can't they interact? Right? Interact or mix together. Right? Sigma orbital generally, orbital mix strongly. Sigma star orbital differ more in energy and mix very weakly. These are all based on calculations. Okay? Right. Now look at here. What I have shown here is that the boron, the B2 molecule. Here it is supposed to be according to the configuration is Diag. But now you see here what I have. Here is your sigma bonding, sigma antibonding. Here because of the mixing, the pi MOs comes down, the sigma MO goes up. As a result, what happened? You have your two unpaired electron. As a result, this is paramagnetic. Right? I hope you got it. Right? The same way you can do it for C2. Right? If you take a C2, we don't have a time to draw all that. You can simply say that you can look at this one. The C2. C2 is, say, for example, carbon is 6. Atomic number is 6. Totally you should have 12 electrons. If you fill that, as I have shown here. Now you see here. Now what do you have? Already 4 electron is gone for your 1s MOs, and you have 2s MO, 2 electron, another 2 electron, and then 2 electron and 2 electron goes here. According to this configuration, that is, if there is no mixing, it should be paramagnetic. Now, if it is obvious that if you go here and see this diagram, now what we have, your carbon, the energy gap is less with respect to your fluorine and oxygen. It's a comparison. So the mixing will take place from between this one, right? What we have, there's a sense talking about the mixing only from boron to nitrogen, because here you don't have a p orbitals, right? So you will have a common MO diagram for lithium to nitrogen, that is Li to N2. So what is the common MO diagram? That is what we are talking about. You mixing your pi, the pi orbital, pi MO comes down. On the other hand, your sigma MO goes up. Here you see here, the same is the case. Now your C2 molecule is basically diamagnetic. So in the case of a B2 as well as in the C2, experimentally observed magnetic moment, magnetic property is diamagnetic, not paramagnetic. It's not simply based on your theoretical filling of the electron. It is experimentally observed that it is diamagnetic. Now, I have given this general diagram. General diagram, what for? That is that you can remember lithium to nitrogen. What is that? You have a sigma G, sigma U, and then you have your pi U, and then your sigma G. On the other hand, in the case of your O2, oxygen and fluorine, what we have is your totally different diagram, normal way of goes here, because there won't be any mixing, simply because the energy gap between your 2s and 2p is too large for considering for the orbital mixing. So there is a separate MO. So now you understand that there are two sets of MO diagram, general diagram, Li2 to N2 and oxygen to fluorine, right? I hope that you are with me. There should not be any confusion, right?
Sir,
Somebody
just
asked a
one
question in the
thing.
middle, right? What was the question? Quickly.
Yes, yes, sir. Sir, before the SP mixing, like the condition for the
Yes.
SP mixing was that. Sir, am I audible?
Annoying.
Yes, sir. Am I audible?
Okay. But let's look at you. I hope you can listen to me, right?
Yes, sir. But am I audible? I had a
Am I
question
audible?
regarding the. Yes, am I audible?
Okay. My system has failed. Okay. Tanmay, what was the question?
Yes, my doubt was that when SP mixing was occurring due to the low difference in energy between the S and P orbitals, then why does that after the mixing the energy of the sigma
No, just
orbital increases?
no. Can you do after mixing? What is that?
After mixing, why does the energy of the sigma orbital increase? Like
I'm
it
sorry,
goes.
my system, my speaker give up trouble. Tell me, after mixing?
Yes, sir. After mixing, why does the energy of the sigma orbital suddenly increase to a high value? That I had doubt in this.
No, right. Basically, what happened is that as a result of mixing, after mixing, the resultant MO has a different energy. What happens? The pi MO's energy is little lower with respect to your sigma MO. It's not that energy is huge difference. Right? I can show you. We have a software package that we can mix these two orbital and show that, but we don't have a time, so we will not be able to do that. Otherwise, we need to have the quantum mechanical calculation, right? This is already proved that there's a mixing, and the pi MO's energy is lower, and then sigma MO energy is little. It's not that it's a huge energy gap. It's little. I mean, just above the pi MO. So as a result, what should happen? You're according to the Pauli exclusion principle, or you are according to the fundamental principle, the electron should go to your pi MO rather than your sigma MO, right? Okay. Now what we have here is that.
Yes, sir.
I'm sorry, my speaker is giving a trouble. Right. Yeah. No, after orbital mixing, that I mean, this is for your lithium to nitrogen and your general. This you can see in the Atkins textbook. Stephen Atkins textbook, you will be able to see that I have taken from there. Okay. Right. Now look at this diagram. Look at this diagram. What we have here is that I have plotted a bond distance versus the valence electron, right? What I get from here, if I make a plot of bond distance versus valence electron, what I'm doing is that, say for example, look at here. What I do is that I am gradually filling the number of electrons. Say for example, here from here to boron to nitrogen, I am adding the electron to the bonding MOs, right? I hope you are with me. Now, when I go further, what I'm doing is when I'm filling the antibonding orbital from here to here, that is from nitrogen to F2 here, RO2 2 minus. What we have, we are basically filling the antibonding MOs. As a result, what is happening? What is the implication? Or in other words, when I increase the valence electron from here to here, say I started from 6, when I go to 14, basically what I do, I'm putting the electron, filling the electron, filling the antibonding MOs. Now here what we have, your bond distance basically decreases up to nitrogen. Right? Why it happened? The incoming electron goes to the bonding orbital. On the other hand, when you are started filling the antibonding MO, the bond length started increasing. Okay, so in between that, whatever is there, you manipulate the number of electrons. The molecule exists or doesn't exist, it's not a matter. You know that oxygen, whether it's O2 minus or O2 2 minus or O2 3 minus, based on the number of electrons there, with in the MO diagram, you can fill it. And then you can predict whether this system exists, what happened to the bond strength or the bond distance or the bond length, you can predict. Okay. Now I put in this in the table. We are not going to read all that. Right. Typically, we'll see here. Now you see here oxygen, 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 and then you have bond order of 2. Okay. Now what we have a bond length of 120 picometer. Now bond energy of 493 kilojoule per mole. Now, what you do is a very simple example. What I do is I convert into O2 plus or O2 minus or O2 2 minus. What is happening, you will be able to understand here, your bond length and then bond energy, and accordingly here it changes. So, whether you know the actual value of your bond energy or bond length, it does not matter. If you know the bond order and the bond length of oxygen, you will be able to predict the other molecules, other oxygen species, say for example O2 plus or O2 2 minus or O2 minus, simply from the MO diagram, right? I hope you got it. Okay. Now, almost at the end of the homonuclear diatomics. This is just to explain you, convince you that there is MOs where you have a bonding and antibonding MO. This is nothing to do with your syllabus. Okay, don't much bother about it. Here, what I'm talking yesterday I mentioned, photoelectron spectroscopy. Right? You may have a question, sir, really bonding MO and antibonding MOs exist there? Because we have not done the mathematical calculations. So some of you may have a doubt. Now, here is a beautiful experiment. What you do is that you take a molecule, say for example nitrogen, you bombard with a high energy, X-ray, bombard with X-ray, say for example, Hnu. Now, you know the atomic orbitals. Now the electron is supposed to get ejected because you are bombarding your molecule with a X-ray or high energy electron, right? Anything can be done. Okay. Now, we have already, you should have studied in physics. Energy is so quantized. Orbitals are discrete. It's not continuum. It's a discrete values. That's what we should have studied in your, I hope, in the particle in 1D box. When you do the Schrodinger equation and then go for a particle in 1D box, and then you will be able to see that it's discrete energy level. Now here I will be able to show a bonding and antibonding MO really exists. How do we know that? if the electron is coming from the bonding orbital, it will give a signature corresponding to that, characteristically corresponding to that energy level, what we call the binding energy of a particular electron. So the fundamental principle is you bombard and follow the kinetic energy of the ejected electron. Ejected electron, you follow it. And then make a plot. This is what I have in a simple plot. You get a signature. This current signature basically corresponding to the particular electron. Here you have a kinetic energy and here you have an intensity. Right now, I quickly show here. Right now, what I have taken nitrogen. You will be able to see here your sigma u, pi u, and sigma g orbital corresponding to the nitrogen electron in the nitrogen MO. Right. So now you will be able to. I mean, no one can deny that. There is no antibonding MO. It's an assumption. No, it is not that. There's a bonding and antibonding MO is there. Each and every electrons in the bonding and antibonding orbitals gives you a characteristic peak. So that's a very characteristic signature for your nitrogen or the molecule that you will be examining. Right. I hope you are with me. Now what we have is that is so far what we have seen is the homonuclear diatomics. That is lithium to nitrogen and oxygen and fluorine. Okay, two different MOs. You have your syllabus contain only the homonuclear diatomics of first four. One example of heteronuclear. If the previous case, what we have seen, both are A, homonuclear diatomic. Now what we are going to see here is, again, there is no quantum mechanical treatment we are going to do. We are going to simply see a MO diagram, how it is there. So this is a heteronuclear diatomic, how this MO can be made, how the overlap takes place. Again, the fundamental principle, that is a linear combination of atomic orbital, that remains same. But here, if the energy is too large, energy between the atomic orbitals of A and B is too large, so you will not have any effective overlap. So there won't be any molecule AB, right? Now look at here. Again, we can treat with the quantum mechanical treatment. I have drawn the wave function, all this one. Here I have put here the phi A and phi B. Why I have not drawn this atomic orbital the same level? Because these two are having two different characteristic signatures, characteristic properties. The energy cannot be same. Say for example, A, this is the energy, here is the B's energy. But one thing we need to keep in mind, the energy gap is not too large for an overlap to occur. If it is too large, there won't be any reaction between these two atoms, A and B. There won't be any bonding between A and B. Right? Now we see here. Now I have given this the only one example that you will be studying, the carbon monoxide. Okay? Little complex diagram. Again, I have omitted the 1s orbital part. I have started with the 2s. You don't confuse anything. The diagram is little drawn with a different way because this is a heteronuclear diatomic. Okay, here I have your carbon. This is corresponds to your carbon. This corresponds to your oxygen. Right? You know the number of electrons. Carbon 6, oxygen. How many electrons? Anybody unmute and tell? How many electrons?
14.
14. How did you get 14? 6 plus? Okay, right. Now what you need to do is you fill up the electrons, right? That is very straightforward, but because you already studied, I mean, this from your class 10, right? That's not a big issue. What we need to remember here is that we need to find out what is the HOMO and what is the LUMO. Right. Now you have your here 2 electron, and then 4 electron goes here to your pi orbital, and then here you go your 3 sigma, that is a 2 electron. Now highest occupied molecular orbital for carbon monoxide is the 3 sigma, or what we call the sigma orbital. Okay. On the other hand, you have the lowest unoccupied is the antibonding orbital. Okay, why I take time to explain is that this molecule will be studying in the case of your bioinorganic chemistry as well as an organometallic chemistry. Okay, so your HOMO in carbon monoxide is basically your 3 sigma, and then the LUMO is the antibonding orbital. A brief explanation. One who inhale carbon monoxide, what will happen to this guy if he is inhaling carbon monoxide? Come on, quick.
Sir, it will bind with hemoglobin.
What will happen to that guy?
He'll
It will
die.
bind.
He will die.
He will die.
He
Why
will
he
die.
die? Why he dies?
Because there won't
It
be
makes
oxygen.
Sir, the carbon monoxide binds with hemoglobin, and that's the transport of oxygen is stopped.
Yeah, because this is unlike oxygen. That's beauty here. You have oxygen that reversibly bind, but this notorious carbon monoxide does not reversibly bind. Is irreversibly bind. Why it irreversibly bind? Oxygen doesn't bind irreversibly. Why? That we will study in the bioinorganic chemistry and organometallic chemistry. What we call is that a back bonding, right? This orbital is very important. These two orbitals are, one is a bonding, donation from the metal to the ligand and the ligand to the metal. As a result, your hemoglobin, bonding of CO with the hemoglobin is very strong, what we call the synergistic interaction between carbon monoxide and iron. If you want to break this, you have to destroy the hemoglobin. Otherwise, you cannot. By the time this fellow will be no more, right? Okay, right. That's all. Here we go. This is the final slide in this bonding part. As I mentioned here, you have a lone pair here, and here you have a lone pair here. That is your sigma is there, and then this antibonding orbitals are empty to accommodate the incoming electron, provided the symmetry and energy matches. In the case of your hemoglobin, your energy level of iron and then symmetry of the orbital matches with the symmetry and energy of the carbon monoxide MO. As a result, a synergistic interaction, the carbon monoxide irreversibly binds. Okay, right. So what we have seen in the bonding part, that is what we have seen. How to build up a MO based on the simple concept. Mainly what you need to understand is the orbital mixing, bond order, bond length, and then bond energy, how it changes. Typically, in the first row, diatomics, lithium to nitrogen, oxygen to fluorine. I think there should not be any problem in understanding this one. It's a very fundamental concept, right? Okay, now let's go here. Now let's go here. What we have is that the next part. Again, is a bonding continues. Is a coordination chemistry, right? You should have studied the coordination chemistry. I want to hear from you very briefly, right? Very briefly. What do you know? At least one or a couple of you. That what did you learn in coordination chemistry?
Sir, crystal field theory of D2sp3 and sp3d2, and 3 types of geometries. One was octahedral, one was tetrahedral, and other was square planar. And we know how to decide which compound will form which geometry.
Okay, that is about right. Yeah, right. Yeah, he narrated in there the coordination chemistry briefly. Anybody else? What? Yes.
Sir, using different theories to predict the electronic configuration and the magnetic moment of different species.
Okay, right. You are going little, advanced concepts, right? Of course, that is in your syllabus. Who comes to your mind when you talk about coordination chemistry? Any scientist name?
Warner.
Pardon? Werner.
Warner.
Werner.
Yes.
What did he do? You should have heard about this primary valency and secondary valency. Do you remember?
Yes, sir.
Yes, sir. He
Theories.
gave those
Right,
concepts.
Yes, sir.
Yeah, we will not be studying all the details. That's very fundamental. So here, what we'll be seeing then, crystal field theory and its application. Metal ions from laboratory to living system. That is, living system is your hemoglobin, right? Hemoglobin. your iron center. Metal ions, how the color changes that you will see. The spectroscopic, magnetic and functional property, new age coordination compound, right? Some of the coordination compound I will show you, particularly your hemoglobin. Hemoglobin is the what? That is the living system. So that's the content of your second part of your bonding. Now look at here. There are 2%, right? I'm not sure how many of you read through your chemistry textbook when you are preparing for your JE or your class 10. So there are these are the 2%, right? Even if you Google it, you will be able to you will be able to see that Jorgensen and Alfred Werner, right? The Jorgensen was the first time, right, proposed something related to the coordination chemistry, and there was a long debate between Werner and then Jorgensen regarding the bonding, how it is bonded together. So there is no concept of your ligand coming and coordinating the metal. We were talking about Werner was talking about the primary and secondary valency. Jorgensen said, I mean, credit should have been given little to Jorgensen, but no credit is given to him because he developed a lot of things, the fundamental. But Werner understood, and then he modified based on what Jorgensen proposed and find out the flaws. And then he completely ruled out what Jorgensen has proposed. At the end of the day, who got the Nobel Prize? Not Jorgensen, but Werner. But it doesn't mean that what Jorgensen proposed and fundamental is not valid. All are fundamentals for the development of the coordination theory by Werner. But he did not get any credit, right? Sometimes it happens. Okay. So we have a valence bond theory. I already explained the crystal field theory. There is a modified CFT is that ligand field theory, and then MOT. MOT I have already studied. We will not go to the advanced topic. Do you remember these pages? Is delay? There is a delay. Do you remember these pages? Where from? Anybody?
NCERT.
NCERT, right? NCERT textbook, right? Already it is there. Whatever I will be teaching, that is mostly from either crystal field theory, not in advanced level. Very brief is there in the, you see here. The limitation of valence bond theory, what I have mentioned in yesterday's class, and the crystal field theory, what I will be teaching, it's already there. It's not something new, provided you read through the textbook of NCERT, right? Again, this is also there, right? So very briefly, 2 pages, around 2 pages, I suppose. I have taken from the NCERT book. This we will study in detail. Okay, now we'll go. I mean, again, it's a repetition of what I have explained you in the previous class. What is the drawback of the valence bond theory? And then why do we need another theory to explain the bonding or the characteristic or the properties of particularly the inorganic complexes, not organic compounds. We are talking about the inorganic complexes. Valence bond theory is good enough to explain the bonding and the characteristic features of organic molecules, right? So basically what we have, you have a ligand and the metal, that is basically Lewis base and the Lewis acid. And then there is an interaction according to hybridization according to Pauli, and that's what we have seen the previous class I have shown here. Main problem is that what we have based on the concept of hybridization is in the valence bond theory, right? So when we are talking about the bonding in inorganic complexes, we avoid talking about this hybridization because the bonding is much more than the simple hybridization, the concept, right? So number one is that it cannot account for the color of the complexes. The number one. Another one what we have is that your magnetic property is predicted wrongly. And as I said, the spectrochemical series cannot be accounted, right? I'm not going to explain you further. Now, here comes the crystal field theory, right? Crystal field theory is not basically developed by Werner or Jorgensen, right? Don't mistake. Coordination chemistry foundation was laid by Jorgensen, followed by Werner. Werner has the primary valency and secondary valency. Then he got the Nobel Prize. Here's the man comes, right? He's the one actually developed the crystal field theory, commonly we call the CFT, right? Crystal field theory. Okay. Now, this is not to explain, this theory was not meant for explaining the bonding or the properties of the inorganic complexes. It is meant for explaining the color of the stone or the different properties of the crystals. Okay. So what it actually crystal field theory talks about? These are some diagrams that I have given. We will come back these colors, right? Basically talks about your d orbitals. Okay, the crystal field theory is completely centered only around the d orbitals, right? I have shown here, right? Yeah, there's a delay is there. Yeah, there is a the d orbitals are there, right? It talks about the only the d orbitals, not the other orbitals, and then splitting of there. Okay, this is what I have mentioned, that the crystal field theory is actually meant for explaining the crystals, basically developed by a physicist, what I have shown in the previous slide, right? To explain the colors of the crystal or the gemstones and so on, right? These are some examples, right? Gemstones over the color in from the trace transition metal ion, right? Doping, what we call the doping of, say for example, Mn plus into the oxide based material. Say for example, yeah, Al2O3 colorless. You do your chromium to it's ruby and so on. All these are all there. Those who study the crystal, the solid state chemistry, or in the physics, the crystal color, you will understand that what are the effect that is coming here. Those who are going for a chemistry, you will study in your solid state chemistry, right? We are not going to here. Now, before going to the crystal field theory, we need to come to the periodic table. Periodic table. What is the periodic table? What we have? We are going to talk about the first row transition elements, right? So the first row, what we have here, you have your scandium and end with your zinc. Okay, right here I have a scandium and the zinc here. So the first row D block. This is what we call the first row D block, right? Now, I don't call these all of them scandium to zinc as a transition metal, TM transition metal. I don't go to call simply because the scandium and zinc are totally different. It's an odd man out, odd elements out. How do I say that? There's a definition for transition metal. The transition metal should have a partially filled orbital in their stable oxidation state. Right? I repeat, the transition metal should have a partially filled orbital in the stable oxidation state. So, in general, we consider the first row separately, and then from titanium to copper, we consider separately. This is titanium to copper, we consider separately. So the transition metal is basically your titanium to copper, not scandium to zinc, because the stable oxidation state for scandium is 3+. There is no partially filled orbital. And in the case of zinc, +2 is the stable oxidation state. There is no partially filled orbital. So the scandium and zinc is gone out of the definition of transition metal. So we'll be talking about the titanium to copper. Why we do that? These elements, that is the titanium to copper, has a peculiar property. We can group together that can be comfortably studied with the help of crystal field theory, right? I hope you read this one. Why do I consider the first row separately and then transition metal? The definition, how it goes. Okay. Now look at here. As I said, already I have explained the plus through oxidation state, right? Plus through oxidation state. And here you have +2 oxidation state. Only copper has a +1 where you can be stabilized with the help of a pi acceptor. So one thing that we can understand from this table is that these elements, what are these elements? Transition metal elements has variable oxidation states. Right? So that you can see here, that is not in the case of your scandium as well as in the zinc. So we will be, whenever we study about the coordination chemistry, mostly we'll be dealing with the first row transition elements. Okay, right. Now there's a simple definition, right? Complex You have a metal ion. It can be 0 or is bonded to a yes.
Can you see the previous slide?
Yeah, there's a delay. Yesterday I used the PPT. There was delay. Today I converted to PDF. Again, there is a delay. Is there? But we,
explain the definition. Copper is the only element.
No, I did not get you.
Sir, please explain this definition. Copper is the only element.
Definition of what? Transition metal or copper?
The copper one.
Yeah. See here, in the case of the copper is the only one, copper 1, right? Copper 1 oxidation state. Without pi acceptor ligand, you can stabilize. On the other hand, right, this you need to, study more, otherwise you will not be able to understand. You have a +1 oxidation state, all of them are there. But in the case of copper, only in the case of copper, I will explain you when I teach you the redox. I will bring the Frost diagram, then I will bring this one. Only copper 1 can be stabilized, otherwise copper 1 cannot be stabilized. If you have a copper 1 without pi acceptor ligand. You know the pi acceptor by donor. If you do not know, wait till I finish the crystal field theory. Then at the end of the day, I will be bringing the ligands to explain you. Without pi acceptor ligand, copper 1 can be stabilized. All other +1 oxidation state transition metal cannot be stabilized without you have a pi acceptor. You need a pi acceptor ligand. So I will explain you how it comes there, what is the implication in the properties when I teach you the redox, the diagrammatic representation of redox potential, as well as I will be talking about the pi acceptor and pi donor at the end of the crystal field theory when we move to organometallic and bioorganic. Okay, right. So transition metal acts as a Lewis acid. I have already mentioned. If that is the case, ligand should be a base, Lewis base. Now you can read this definition, right? If you want to read more on ligand in chemistry, there's a beautiful review article. Yeah, brief review article, a fascinating review in the journal called Polyhedron, the 1993 first 7 pages. Okay. Again, I'm not explaining the definition where from this comes all the Latin, all this one. You can read through it. It's very simple. Okay, right. Now we'll come here. What we have, as I mentioned, that Lewis acid and the Lewis base. These are the two things that we are going to consider in the case of your coordination chemistry. Right, a coordination compound that contains one or more complexes. Say, for example, these are the examples. You should have studied your isomerism, the nomenclature in your class 11, 12, of course, in JE preparation. So we will not be studying all that one. At the time, you should have studied this, the basic definition of coordination. What is coordination compound and what is the coordination complex, right? Coordination compound that contains one or more complexes. Okay, you say, for example, coordination isomer, right? Coordination isomer, right? You have two different complex, coordination complex form an isomer, right? You can see that. Okay. Now I have given a 3 to 4 different geometry or the shape of the molecule. Here what I have a linear. Here I have a square planar, and here I have a tetrahedral. On the other hand, I have an octahedral here. So who decide this one? Am I deciding this one? Either this ligand is deciding or the central metal atom is deciding. Now you will say that, sir, let us go to VSEPR theory. There we will be able to, based on the hybridization, we will predict the geometry or shape of the molecule. Yes, that is well and good, but that give you a geometry, but that doesn't explain the nature of bonding. It doesn't explain the properties of the molecule. So there's a linear or your square planar or your tetrahedral and octahedral. Now the crystal field theory will give a little flavor. It's an attempt to explain how this geometry can be brought in terms of a theory and bringing these ligands and metal together, and then explain particularly the color of the complex and the magnetic properties. These are the two things that we are going to learn, right? Okay, right. I will give you a 2-3 minutes break. 3 minutes break is I think it's enough, right? 3 minutes break, and then we will start, right?
Hello, sir.
Yes.
Hello.
Yes.
Will you share
Yes.
the slides with us?
Pardon?
Hello, sir.
Yes.
Sir, the slides have not been uploaded of inorganic chemistry.
Yesterday I told, right? Once I finish today's class, by this evening, you will get the bonding, crystal field theory, how much I finished, I will upload it.
Oh, okay,
Right?
sir.
Before finishing, if I upload, you will not come to the class. That's known for, right, years after years. Usually I do that. By this evening, I will upload. Okay?
Okay, sir, no problem.
Now, after 2 minute break, you will meet. Okay, let's start. So what we have here is that crystal field theory, the crystal field model, right? You can read. I think you should have read already. They're basically largely replaced by valence bond theory. As I mentioned that this is the person who proposed Bates in 1929, and then modified, and then it comes to ligand field theory, what we call the LFT. We will not be studying. You will not be studying LFT. And now, what is there is what we have here is that the basic fundamental. I think you should have studied already, but I should explain you very briefly. What we have is that it's a purely ionic model. The crystal field theory is not explaining or providing an explanation for bonding, but it simply talks about your color and the magnetic property. So you will not be able to understand anything of the bonding in the inorganic complexes with the help of crystal field theory, but you will be able to understand the properties, some of the properties, say for example, magnetic property or the spectral property, the color of the complexes. So what is all about crystal field theory? It's quite straightforward. It's a purely ionic model. So metal center, what we have is your positively charged. Say for example, you have a Mn plus. Okay, this is a metal center. Now the ligands that are coordinated to the metal center, say for example, an octahedral complex. Okay, so an octahedral complex. Let me draw this one. Okay, now look at here. What we have here is that I have a metal Mn plus, and then this is coordinated with the 6 ligand, L. Okay. Now what we have here is this is a positively charged. The fundamental principle is that is purely electrostatic. Then if that is the case, all these should be negatively charged, right? L minus. You have a Mn plus and then Nl minus. These are held together by according to the crystal field theory. It's a simple electrostatic model. That's a simple electrostatic interaction between this Mn plus and the ligand. That is what we have here. Okay. So does it mean that all the metal complexes are electrostatically bound? We have molecules. We have metal complexes. Say for example, M hexaco complex 6. You have a N plus. It is there already. That is, you have your metal hexaco complex. What is a neutral ligand? How it can have an electrostatic interaction? Yeah, what we will listen, we talk about the dipole. Okay, in general,
NiCO4.
Pardon?
Sir, Ni and CO 4 times. That is also neutral.
Yes, NiCO, tetracarbonyl 2 plus, right? Again, neutral. So how do we explain all these one? Yeah, there what we call the dipole and other interactions are there, right? So basically what you need to understand here is that electrostatic model. That's what I have given here, the pure electrostatic model. Ligands are considered as a point charge, right? Not necessarily simply a negative charge. It can be a dipole, right? It predicts the splitting of d orbital. As I mentioned there, crystal field theory is centered around only the d orbital. It doesn't talk anything about the s orbital or the p orbital. You can understand the spectroscopic and magnetic properties. So you have octahedral complex, tetrahedral complex, square planar complex. These three are the main player. Main geometry that we will be studying. How we can explain the hexa coordination or your tetra coordination in the tetrahedral and in the square planar. You will be able to understand with the help of crystal field theory, but not the bonding. Again, I repeat that it is the spectral property and the magnetic property. Okay, now it comes here, right? So what we have here is that the orbitals. You should have already studied. You have your dA, YZ, XY, and XZ. Those who want to see the actual model, usually if it is a physical class, I used to show these all the models and all. In the camera, you will be able to see here. That is one of the d orbitals. And what we have here is that what I have is the dz squared orbital. That's what we have here. And dx squared minus y squared. So that how this dz squared orbital, just for your information, that is basically a linear combination of dz squared x squared and dz squared dy squared. It should have been written by this way for simplifying what we have a dz squared orbital. Okay, so you remember that this is very important. There's a d orbitals because the crystal field theory is centered on the d orbital. You have a 3 orbital here. I have a 2 orbital. I have classified in the 2 with a purpose, right? Now, here what we have is the central metal. As I have drawn here, right in the previous slide. Here I have drawn here metal and the ligand. Now what I bring here is the actual model, octagonal complex I am bringing. Okay. Now look at the model. What I am showing here. There I have a gray color central metal, and I have put either you consider this as orbital or ligand, whatever it may be. It will be all right. Okay. So this is basically what we have is the octagonal model, right? So when we talk about the crystal field theory, what we're going to talk about is that crystal field splitting of d orbitals. Okay. Now what we have is that now first what you need to consider is that you consider a cube. Okay. You can see in the camera I am showing that this is a cube. Okay. So inside the cube, this has to make you understand. Inside the cube, what I have a central metal. Okay. Central metal. Assume that these are all orbitals. Okay. There are two types of orbitals are there. Okay. That is what we have. What I have shown here. Here is a one group of orbital. Here is a one group of orbital. YZ, XY, and then XZ. And then the down Z square and X square minus Y square. There are two group of orbitals. If you carefully look at the diagram, you will be able to distinguish. You will be able to find out why I have classified into two. Right? Can anyone unmute and tell me why did I do that?
Sir, it is about the direction of the approach of ligands.
No, don't bring the ligand now. Other than look at the diagram and tell me why did
So
I
like one
On the axis and
like one
in middle of
category
the
is
axis.
facing directly the axis, and the others
exactly
are
right. Very right. What we have here is that you have a central metal. There are one group of orbital. Their orbitals are lying in between the axis. Okay. But another group of orbital that is lie along the axis. Okay. So that is why we classified in the two group of orbital. Now we'll go here. Right. Now you have, this is the model that we have. I have shown here. Now what we have is that. Now look at this diagram and the model that we have. Now what we have, you need to see that. Now you have a metal center. Let me here metal center. Now what I have here is this complete here octagonal field. Now what I do is that, just to make you understand what I do, I am bringing a 6 ligands along the faces of the cube. Okay, I hope you are getting. That is the 6 ligands. 6 ligands are coming along the faces of the cube. Here. Right. Now assume that here this is a metal center. Here I have a metal center, and these are the orbitals. Here two group of orbitals are there. One is 3 are in between the axis, and the 2 are along the axis. Now I am bringing the ligands along the faces of the orbital. Can you tell me which orbital will have a direct interaction with the incoming ligands?
So the orbitals on the axis.
Orbitals that are on the axis. Right? Now look at here. Now what I did, I classified them. Earlier I have shown there. Now I classified this is the EG orbital and then T2G orbital. They are lying in between the axis. Here it is lying. But here what I have, this is along the axis I have. Right? These are along the axis, the EG. How do I say that? This is E is a doubly degenerate, and the T corresponds to a triply degenerate. Now what is meant by G and G here? That again goes back to our symmetry. That is your gerade. That what we have seen earlier. Gerade. Right? If there is a gerade, here what we have in the case of octahedral, one thing is very interesting thing. One is very common. That is here, it has the center of. Can anybody complete center of?
Inversion.
Center of inversion. Center of inversion is there. Octahedral geometry that has a center of inversion, right? Now, I hope you understand. Now, assume this model, there's a cube, and then how these ligands are approaching along the faces of the cube, and what are the orbital will have a direct interaction with the incoming ligand. Now here, right? What I did is that, can we do that? Can we do here, right? What we do here is, you have you have your d orbital. Okay, this is a d orbital. Okay, now this is the spherical symmetry, what we call the spherical symmetry. Now what we have is that, okay, right. Now what happen is this is split into two parts. Here it goes your T2G, that is in between the orbitals, in between the axes. What I call is a T2G. On the other hand, here I have an orbital that is EG. There is some delays there. EG orbital. You have, this is along the axis. So basically, when this kind of a splitting takes place, when I bring a ligand along the faces of the cube, now orbitals that are along the axis experiences more repulsive interaction compared with the orbital that has that are lying in between the axis. It does not mean that T2G orbital does not experience any interaction. It does experience, but the interaction is less with respect to the EG orbital, because EG orbitals are lying along the axis of on the approach of the ligand. Now you know that this is what we call 10 dq, right? 10 dq we call that crystal fields, the energy gap between this one we call it 10 dq. Now here, say for example, I have a say 3 electron. Where this 3 electron will go? Obviously here it will go. Again, we'll talk about the strength of the ligand. When the fourth electron, when I have a 4 electron is here, the 4th electron, where it will go, whether it will go here to the T2G orbital or the EG orbital, that will be decided by the nature of the ligand. Okay, I hope you got it. Now we'll go here. Now look at here. I have already put here. I hope you got it, how we are splitting the diagram. This is my octahedral, the cube that I have shown the central metal and the ligand that are approaching. Now what we have in the octahedral field, what I have the splitting of the d orbital. This is a 10 dq. I have mentioned the previous slide. That's a 10 dq, or what we call the del O, not del 0. It should be del O. Okay. This is the EG orbital. Doubly degenerate. 2 orbital. Who are the orbital? That's the Z squared and X squared minus Y squared. Now, from the barycenter, we can divide that. This is a minus 0.4 del O. Here what we have is that plus 0.6 del O. Okay. I hope you are getting. So how do we get this? Right. I mean the splitting of the orbital, and then orbital that is along the axis rise in energy. On the other hand, in between the axis, the energy is little less. As a result, what we have drawn here. This is the T2G orbital, right? I hope you understand. That is basically this energy gap is basically from the barycenter. What we call the barycenter, what we say 0.6 del O and minus 0.4 del O. This is very important when we are calculating the crystal field stabilization energy, right? So we'll come to that. Okay. Now what I did is I put these complexes. I divided the complexes into 2 categories, right? There is no animation. Really, I used to have animation because of the delay in the PPT. I did not use my PPT. I have the PDF version. Look at the diagram. Okay. What we have here is starting from D1. D1, here is your D1, that is the titanium 3+, and then D2, and then goes on D3, D4, D5, D6, and so on. It goes here. Here, what we need to understand basically, how do we fill up the electron? Up to D3, there is no problem. When the D4 is coming, the 4th electron is coming, say for example, D1 to D3, there is no issue. Because, say for example, let me put here, though it takes time for the benefit, I just show you the filling of the electron filling. This is your T2G, this is your EG, right? Up to D3, there won't be any problem. When the D4 comes here, as I mentioned the previous slide, here it 1, 2, 3. Now the fourth electron, where it's supposed to go, whether it should go here or go here. Say for example, it goes here. That is depending on the nature of the ligands. And whether it's a weak field, weak or strong field. And then we call it a high spin and low spin complex. Okay, whether it is a high spin or low spin complex, that should be decided by the nature of the ligand. That is whether it's a weak field or strong field ligand. Right? Now look at here. Again, there is a delay. Just hold on a minute. Right. Now, so what needs to be know that there are two things. You have your del O, and then what we have is your pairing energy. Okay, there are the two things are important. Here I have mentioned briefly. We put here, right at the bottom. The del O is less than the pairing energy. Del O is greater than the pairing energy. What we talk about the high spin and low spin complexes. Say for example, here I have given iron hexaqua complex, and then FeCN6, two complexes I have given. As you should be very familiar, water is basically your weak field ligand. On the other hand, Cn minus is a strong field ligand. As a result, what happened? The energy gap changes. Then there is a filling of electron. It follows in a different way. So D4, there are two possibilities. One is the high spin. That is your high spin complex. Here, all are given in the top. All these here are high spin complexes. And then another option is there. You have your low spin. That is coming from D4, D5, D6, and D7. That is your D4 to D7 can either have a high spin or you have your low spin complex. When you go to D8, we don't talk anything about the spin at all. Because it already has 8 electron, there is no possibility for high spin and low spin. Right? I hope you are getting. The D1 to D3, yeah, only one configuration. And then from D4 to D7, what we have? We can have a high spin or a low spin. Again, D8 and D9, what we have? We don't classify them as a high spin or low spin complex at all. Okay, again, I'm going back. If you see that once again there is a delay. There is a delay is there. You can follow here. That is your D4 to D7, right? D7. What we have here is that D4, D5, D6, and D7. D7. We have a two set of the spin. High spin and the low spin. Okay. Now let's go here. What's the implication? Because basically we are going to talk about the properties. We'll come to the crystal field stabilization energy little later on. Then, before that, we'll talk about it. So here, say for example, I have a titanium hexaqua 3+. There I have a D1. Only one electron is there. Okay. Only one electron. That one electron, obviously, it will go to the T2G orbital. There is no other way. Right? Now, assume that I have this complex in a test tube. Okay. I have the complex. Now we are going to talk about this energy level. What I mentioned, the CFS, crystal field stabilization, splitting energy, right? This is now, if the energy gap is in such that this electron can be excited to the higher energy EG orbital with the help of your visible light. Okay, visible light. Then there is a transition. That is the visible light, the room light, that is sufficient enough to excite this electron to go here. How it is possible? Your energy is sufficient enough to excite this electron to here. The energy gap is such a way it can excite, and then what will be absorbing the color? You know the color wheel, right? You should be knowing the color wheel with GR. right? It absorbs one color and you observe another color, right? Say for example, if you have your color wheel of this is absorbing a color. Say for example here, what is the color you will observe? Can you, anyone? This is absorption.
It's a diametrically opposite color.
Yeah, what do we call that color?
Complementary color.
Complementary color. You will get a
Complementary
what
color.
you see is the complementary color. The complementary color that you will be seeing that one. So now you can see here. Now this is the energy gap. Now this is the spectra. This is the spectra that I have drawn here. What we have is that here is a wavelength and here is the absorbance, right? Those who are in section 1, I will be taking your first year lab. There I will be explaining you this in the, there's one experiment related to this measurement. I will explain. What we have is the wavelength versus absorbance. Here is your lambda max. That is a wavelength at which it gives the maximum absorbance. Okay, that is basically coming from where? This energy. What is that energy? Crystal field stabilization energy. So if I want to find out the lambda max, the wavelength at which it absorbs, it gives the maximum absorbance, is basically directly coming from the energy gap between your T2G and EG orbital. So who decides the excitation? The energy gap and the energy of the light that is available with you, right? So there is what we call that, say for example, Beer-Lambert's law. Let's not go there. Now what we have is that, yeah, this is simple, titanium X aqua. Your del O is a 20,300 centimeter inverse, corresponding to the energy of 243 kilojoule per mole. It is stabilized by minus 0.4 del O. Then you have this is a minus 97 kilojoule per mole. That is, this complex is stabilized to the extent 97 kilojoule per mole compared to the hypothetical spherical field. Due to that, this is coming because of the crystal field splitting. The extra stabilization complex, what you call the crystal field stabilization energy, right? I hope you are getting what I mean. Actually, I mean, a lot more is there in the CFSE. You need to basically calculate the CFSE. If I know the configuration, say I have a D5 configuration, I should know whether it's a high spin or low spin. Then I can calculate the crystal field stabilization energy. Let's go here, right? Crystal field stabilization energy, the D4, right? I have already mentioned how do we put the D3 up to D3. There is no problem because it will go to the T2G orbital, obviously. When you have the fourth electron, the D4, there are two possibilities. That is, you have either it can be T2G4. No, let me put in the other side. T2G4 or the T2G3 EG1. Now, based on this, your crystal field stabilization energy will change. That you keep in mind, right? Now, what we have here is you have a minus 1.2 del O plus 0.6 del O. That is one electron is here. Here is a 3. 3 into minus 0.4, you have totally got minus 0.6 del O. On the other hand, here you have your minus 1.6 del O plus one pairing energy, right? Pairing energy is very important, right? Because if the electron has to pair, come and sit in this orbital, it has to overcome two things, right? It has to exchange the spin and it has to overcome the Coulombic repulsion. There are two things. One is exchange of the spin that needs energy. Second one is your Coulombic repulsion, that energy. This electron, if it has to go to this orbital, it has to pay the price of exchanging the spin and also paying the Coulombic repulsion. I hope you got it. How do you calculate the CFS? So now you can read this. What is the pairing energy? The pairing energy is not an experimentally obtained value like del O, and is the same for a metal ion irrespective of the ligands. It's made up of a two term I already mentioned, right? Inherent Coulombic repulsion, I already mentioned, repulsion, and then exchange energy. That's the two things that I have mentioned. It cannot stay there with the parallel spin. It's supposed to be in an anti-parallel orientation. right? So a pair, the P is a sum of Pc as P, that is your Coulombic as well as your exchange energy. So even an electron has to go and pair that, what's supposed to be done, a cost that needs to, that the electron has to pay, that is the Coulombic as well as the exchange energy that has to be paid. Now, look at here. I think I don't need to explain further, right? I'm talking about the D5 system. D5 system. D5 system. What we have here is that you have a pairing. I need to write whenever we are talking. Please, listen carefully. Whenever we are writing the crystal field stabilization energy, it is mandatory. It's a must to provide your 2p. That is minus 2 del O plus 2 pairing energy. Here there is no pairing, only here is taking place. That's why we note that there's a 2 pairing energy. On the other hand, now when we come here, now this is the 6 and D6. D6, definitely one electron is already paired. Okay, I hope you are following. Right? Are you with me? Yes? Yes. Right. Now what we have here is that when during the crystal field splitting, now what is pairing takes place, what we should write, this is the correct one. Right, correct one is what? This is the correct one. This cannot be, because already one electron, 2 electrons are paired up. So we should not show here as a pairing. So only 2p, that's minus 2.4 plus 2p, right? Okay, now I mean you can read through the stability that results from the placing transition metal ion in the crystal field generated by set of ligands. Yeah, whatever I have already mentioned that, right? We don't know much. Important thing is that CFS. That is. Now, case T2G set becomes a lower energy with respect to the barycenter. Already I explained. And occupying this T2G orbital, metal ion is more stable relative to the barycenter amount is known as a crystal field stabilization. I think we don't need to waste the time. Already I explained everything. Now I put in the table. As I already again I mentioned, D1 to D3, we don't have it. No problem. When we comes about, don't bother about the magnetic property now. I will come to this later on. Okay. And then we are talking about the D4. There you will have your the low spin and then high spin complexes, and then D5, and then D6, and then D7. Of course, D8 and D8, right? Doesn't come. D10, obviously you will have a 0, right? Zinc 2 plus is D10. Crystal field stabilization energy is equal to 0. There won't be any impact on that. So we don't consider zinc 2 plus there. Okay, right. Okay. Now, so far what we have seen, that let me explain once again, little bit of, right? What we have seen, I have a d orbital here. This undergoes split into 2. That is, one is a Eg. Another one, what I have is that my T2G. So this energy gap, what we say, a del O. Now I'm going to teach you what affects this del O value. The crystal field stabilization, who decides this one? That's what I'm going to talk about. Okay, number 1, nature of the metal ion. Right, nature of the metal ion. What I'm talking about, Mn plus. Number 1. Number 2 is the oxidation state. Right, say for example, nature of metal ion. I'm talking about the larger the metal ion, larger the del value. I will give you an example, the coming slide. I will get back to you one by one. Second one is the oxidation state of the metal. Because we are talking about the electrostatic, definitely the 2 plus and 4 plus cannot have the same impact. The 4 plus will have a more impact in the crystal field, splitting with respect to your plus 2. And then, more importantly, the number of ligands. How many ligands are coming to the cube? Right, that I have shown. And then the fourth one is the relative strength of the ligand, what we call the spectrochemical series. So 4 things that comes to the picture when we are talking about the splitting, crystal field splitting of d orbital. Number 1 is the nature of the metal. Number 2 is your oxidation state. Number 3 is the number of ligand. Number 4 is the relative strength of the ligand. Now look at here. Read through. Let me sip a cup of water and then I will explain. Right. Read through it. What I am talking about here. Okay. What I'm talking is here is the nature of the metal. That is basically here 3D versus 4D versus 5D. That is 3D, 4D, and 5D. How it affects. I have given an explanation. Example. I mean, trisethylene diamine cobalt complex, which has a del O values are 23,200. On the other hand, rhodium, the same ligands, the ligand remains same. Oxidation state remains same. I am changing from 3D to 4D to 5D. Iridium. What we have a significant increase in the del O value. Here it's initially it is a 50% increase and then it's a 25% increase. What is the reason? Second and third row tensile metal we have a greater tendency to form low spin complex. Low spin complex. Now we can easily say that, right? Second and third row will form a low spin complex with respect to, again compared with the first row. That is a 3D. What is the reason? Around a large metal ion, a given set of ligand experiences a less steric crowding. I hope you're understanding. Right? A small ball versus a big ball. Okay. The steric factor that comes into picture. As a result, your splitting goes here. You can read that. More closer, larger will be the splitting. Yeah, those who will be studying chemistry, you will study this more in the case of when you go for the 4D series and 5D series. When you talk about the lanthanides, actinides, you will study more on that. The metal size is too big. As a result, we not only talk about the 6 coordination, we'll talk about the 8 coordination, 10 coordination, 12 coordination, right? So here what you need to remember is that as the size of the metal center increases, the crystal del O value increases. The consequence is that you have high spin to low spin complex. What is the reason? Yeah, if it is a small, a steric crowding, larger, less steric crowding, the splitting is more, right? Okay. Now, the second one, right? Second one, what we have is the oxidation stage, right? Oxidation stage. Now look at here. This is quite straightforward, right? Very straightforward. I have a 2 plus, there I have a 10,000 centimeter inverse. Here you have your 3 plus, a significant increase that goes to 22,900 centimeter inverse. What is the reason? Can anyone unmute your microphone and tell me? Otherwise, I am talking to the screen. Hello? Are you with me?
Yes, sir. Yes, sir.
Nobody is answering. What is the reason? Unmute your microphone and tell. Rajdeep Maji.
Yes, sir.
Sogam. Rajdeep, tell me what is the reason? No. Sogam?
Sir, are you calling me?
Yes, Sogam Chakrabarti.
Yes, sir.
Yeah. What is the reason? Please respond.
Sir,
Please respond. Otherwise, I am talking to the screen.
Yes, sir. What happens is basically when the charge on the metals increases, it basically attracts the ligands with a greater force. So the ligands give more repulsion to the electrons in the EG, and then the increases.
Okay, thank you very much. Right, ever simple electrostatic. Here you have a 2 plus chromium, ligand remains same, and then you have a 3 plus, an increase, significant increase, 14,000 to 17,400. Right. So first one was the nature of the metal center. Second one is the oxidation state. The third one is that what we have here is the important, right? The number of ligands that is coming to the. We will be studying in this. Yes.
So del is the energy or wavelength.
Pardon?
It is wave number.
So
In
del is
1
the
by
energy or
1 by
wavelength.
lambda.
I say the centimeter
1 by lambda,
inverse.
the wavelength number.
Centimeter inverse.
Wave number, I guess it is.
Yes, a wave number. Obviously.
Yeah.
I thought you know this, right? What we are talking about, all the values are given in centimeter inverse, right? Not in nanometers. Okay, right. Coming here. Now, what I have here is I got typical two cases, right? Now, this is my 5 d orbitals. Okay. In the octahedral field, there's a free. In the octahedral field, as I mentioned there, it's split into 2 parts. That is your T2G and UG. Okay. Now, if how many ligands are coming in the octahedral field? Totally, you have at 6 ligands. 6 ligands are coming. Now, I reduce the number of ligands to 4. So, either in the case of a tetrahedral field or in the case of a square planar. Square planar will come later. It will take a lot of time for me to explain. Here we will see that the number of ligands, how it affects the del O values, del value. Now, in the case of your tetrahedral, I hope everybody understood the octahedral, how the 6 ligand is approaching to the metal center along the faces. Now, here what we have here is, I have only the 4 ligands. The 4 ligands are coming along the alternate faces, alternate corners of the cube. Alternate corners of the cube. Okay. As a result, your interaction, I will explain you the tetrahedral splitting little later. Here, let me explain only how the number of ligand influence the del value. Okay. So here, what we have, I have only 4 ligands. Here, I have a 6 ligands. Right? Obviously, square planar also 4 ligands. Now, what I have here is, because the number of ligands that is coming to in the case of your tetrahedral is less. Now, the crystal field splitting is less with respect to your octahedral. Or in other words, what I say, the extent of splitting is less in the case of a tetrahedral with respect to your octahedral. Okay. This diagram I will bring it here again. It's coming the alternate corners 1, 2, 3, and 4. As a result, what will happen is that just reverse the split. The ordering of orbital will be just the reverse. Okay. I will come to this little later. Now, in the tetrahedral field, what is the del value? Del tetrahedral equal to 4 by 9 of del octahedral O. On the other hand, when you go here to the square planar geometry, the value is too high, right? I will explain you how this I'm able to get this delta SP is almost equal to 1.74 del O. Later on, when I talk about the square planar and Yondeller distortion, at the time I will explain. Here, briefly, my next slide will be tetrahedral, right? Now, here what we have? We have the tetrahedral field. You have an alternate. Okay, so tetrahedral, you are less than the del O. So the square planar greater than the del O. That's what we call the almost 1.74 times of the del O. Now come here. Okay. Now what I have here is that now let me show the model and you can look at the screen also. Now in the camera, if you want to see that, you can look at here. What we have is that this is my metal orbital. Now it's the cube. What I'm bringing is that, let me leave it here. Now what I have in the cube, not along the faces of the cube, I am bringing the ligands only along the alternate corners here, leaving this here, leaving this here, and the same way by that alternate corners as I have shown here. Number 1, number 2, number 3, and number 4. 4 ligands are coming creating your tetrahedral geometry. Now what happened? A crystal field splitting takes place, but what happened here is, let me explain you. Though it takes time, goes here, it go here. Here what I have is my EG. I don't call it as a EG. Here I call it is this is my T2. This distance, what I call this del tetrahedron, right? Now I want to hear from you, right? This is the d orbital. In the octahedral field, what I did, I put here, I split into two, and then here I have the T2G, and here I have the, again, there's a lot of delays there, EG orbital, right? Okay. This is your octahedral. This is what TD, that's a tetrahedron. Okay. One of you tell me, I will call someone that those whose name is visible to me, right? Sushmita, right? Sushmita, can you tell me, why did I write E instead of EG? And why did I write T2 instead of T2G? In the case of my TD, that's a tetrahedron. Sushmita? Can you hear me?
Yes, sir, we can hear you.
Yeah, right. I don't want Sogam always responding. Nah. Yeah, I mean, I want others also respond. Right. Abhishek Das, please don't be silent. If you're silent, I am talking to a screen. Anuj, my goodness.
Yes, sir. Yes, sir.
Who is that?
Anuj.
Anuj, tell me, why did I
Sir.
write E instead of EG, T2
Sir,
instead of T2?
It is not symmetrical, sir.
What is not symmetrical?
It's,
Correct,
in
correct.
case of tetrahedron.
Well, symmetrical. What do you mean by symmetrical? Little bit up. Be confident. Even if you're making mistake, no problem. You're very close to the answer. Tetrahedral geometry lacks. Anybody? Sogam?
Center of symmetry.
Center of symmetry, right? Center of inversion is not there.
It
So
is not shaded.
yeah, right. So we won't write EG or T2G, right? Don't make mistake. Right? Many students make a mistake of this one, right? Because octahedral is EG and T2G is there. Okay, let's go and write on tetrahedral also. No, completely wrong. You'll get 0 mark, right? Now we go E and then T2 orbital. Okay. So now why this E orbital came down and the T2G has gone up? Rajdeep Maji? No.
Sir, can I answer?
Yeah, so come answer. To save my time.
Sir, in tetrahedra, what happens is the ligands they approach between the axes. Like the orbitals that are present in between the axes, they go higher up in energy.
Right. So as a result, because your ligand is approaching alternate corners, now you can imagine, as I have shown in the cube, and then place your deep metal here, and then assume the orbitals, how it is a position, and then you can easily, not to mug it up, right? So the T2 goes up, and then E comes down. Okay. Now, that is about the tetrahedron. That is simply we call the TD, right? TD, that's basically coming from the group theory, right? Don't bother. Now coming to the square planar, what is happening? What is happening in the square planar, right? It's little complex, little complex. I will briefly explain, and then I will go to that. How much time I have? I have 15 minutes. Okay, right. So what we have here is, now let me explain. I will come back to this square planar. I will explain you very clearly in the Yandel discussion. What we have here is, now look at this the model that I have shown the camera. Okay, so what I'm doing is that I am taking out, pulling up of these two ligands from the metal center. Right? Assume that initially it was an octahedral ML6. Right now I'm not considering the metal and orbital. I'm considering the ML6 complex. Now I remove this. Okay, there is no ligand. Right? This is a square planar geometry. How did I get this? There is no ligand to interact in the faces, the two faces, the up one and then here. As a result, Now the ligands, there is no ligand. That is R. What we say is that when we talk about the distortion, I will come in later, Yandel distortion, the interaction will be weak. Here there is no ligand to interact with the orbital that is along the faces of these two faces, right? Say for example, I assume here, here and here, there is no ligand at all. As a result, your crystal d orbital splitting pattern should change. Am I right? I hope you're getting. Basically, I had a 6 ligands that is coming through all these phases. Now I don't have a ligand on one of this phase and this phase. As a result, there must be a change in the crystal field splitting pattern of the d orbital. That's what we see here, right? How do we see that? This is Z axis, Z, right? Z axis. Along the Z axis, I don't have any ligand, right? Along the no ligand. As a result, what are the orbital that has the Z component will decrease in energy because there is no interaction, nothing is there to interact. If you look at very carefully, you will be able to see here. XZ, YZ and Z squared are and lower energy, but on the other hand, the X squared minus Y squared, XY are little above. Don't think that is 1 kilometer apart, right? Nothing will happen like that. So you will be able to, I have marked here, right? I will explain you the square planar later when I teach you further. Okay, this is whatever here I explain is to make you understand the number of ligands that is coming to the metal, approaching the metal center, how it influences the del value, right? Okay, now you go here. The strength of the ligand, right? How many of you studied the spectrochemical series? Everybody should have studied because that is in the that is there in the JEE syllabus. I hope, right?
Yeah. Yes.
Yes. Nobody can deny it because I have the NCRT book. NCRT book itself says that you have your spectrochemical series, right? Some of you may think that it's all old songs, sir. Why sir is teaching? So I will see that when I ask you to write the assignment and ask you to write the exam, you will make a lot of mistakes, right? Though you have already studied, it is the portion that we need to study in details to make you understand. Okay, to make it brief, the strength of the ligand. I have shown 3 complex, chromium complex. One is ethylene diamine, another one is oxalate, another one is fluoride. Okay. Now, if you look at this is the spectrum that I have shown, right? The spectrum. What is the spectrum talking about? The color of the complex. I have mentioned. I have shown earlier, right? Here is your wavelength. Here your absorbance, and you get something. This is what I have mentioned here in terms of frequency. I did not put in terms of wavelength, centimeter inverse. I put it here. Now, what I want to say, right? You may say that, sir, what you're talking about, your frequency and all. I'm going to talk about the splitting, the orbital splitting. Say, for example, it go here, here, and here. We are talking about the octagonal. This is your T2G. This is your EG. Now, this energy gap decide the wavelength at which it absorbs. As I have mentioned a couple of slides later. Now, who decide this gap or who decide this one? That's what we have been studying. The strength of the ligand or nature of the ligand. Nature of the ligand that decides. What it decides is a weak field ligand or strong field ligand. Ethylene diamine is a strong field ligand, as you know that. As a result, your frequency is here. Now, oxalate falls in the middle. Let's see a fluoride. You know that halides are a weak field ligand that goes to far end. Oxalate falls in between, right? So who is deciding this color now? This color, this color, this color. Who decides? Sushmita, who decide? Sir is deciding or somebody else is deciding? Am I deciding? Chirag Ghosh, I hope you are listening to me. See, I put the attendance drop to somebody else. Raise the hand. Bajaj Aniruddha. Tell me. Yeah.
So ligand is
Pardon?
deciding.
I did not get you. Ligand is deciding, right? So energy gap is decided by the ligand. What is the strength of the ligand? There's a weak field or strong field that is decided. That decides the energy gap, which in turn decides the color. That's very important. So if I know the strength, I will be able to qualitatively pinpoint, tell that this complex will have this color based on your color wheel, right? I hope you got it. Okay, now look at here. Right, I have put some pictures. Yeah, again, there's a delay. The spectrochemical series. I surprised that the network is problem or team problem. Okay, now here you are. You have your halides here. And here you have your strong field carbon monoxide. Okay. Now what we have, this is one complex. This all I will explain later on, right? Halides, sulfur donor, oxygen donor, nitrogen donor, and Cn minus and CO. Right. The cobalt, here you can see that the photograph that I have shown here, starting from cyano, Cn minus, going to carbonate, I. You have a almost colorless, and here you have a beautiful dark green color, right? This is A2C. Here the A is, this is a colorless complex, that is a Cn minus. Cn minus. But on the other hand, here I have a carbonate complex, CO3 2 minus complex, that is a I. Okay. Can anyone tell me why this color is, the Cn minus is colorless? Anybody? Let me again ask Susmita, you are around? Or you do not want to answer? Abhishek Das, Abhijit Singh, Anal Jodi. My goodness, you are.
Sir, is it because it is a sigma donor pi acceptor?
Let us not go to there. I mean, simply tell it in terms of the strong field versus weak field. Of course, that is the acceptor donor concept will come. I mean, let us not discuss now here. We will simply talk in terms of energy gap. The Cn minus is a strong field ligand. The strong field ligand. As a result, what happened is that the energy gap is too high. The energy that is available in the visible light is not sufficient to excite the electron from your T2G orbital to the EG orbital.
Yes, sir. And there is pairing of electrons.
I hope you understood. Yes?
Yes, sir.
Right. Okay. I'm not going. Many of you are not responding.
Sir, can you explain that point once again, sir?
Once again, right. Now what I have is, just hold on. What I have, let me pull out another page. So what I have, this is my d orbital. Split here the T2G, and here it goes the EG. Now what I have is in the case of a carbonyl or Cn minus, CO or Cn minus, what we have is that energy gap is too large. What is here is, I have a say, for example, I have an electron here. The visible light, I say that this is almost colorless complex. Colorless complex. Why it is colorless? The energy gap is too large. The light that is available, the visible light, because we are looking at the naked eye, that is colorless. That's a visible light we are looking. The visible light energy is not sufficient to excite any of this electron to this orbital because the energy gap is too large. So as a result, what we have, this it should be colorless. Here, I'm not talking anything about the charge transfer. Don't confuse. I'm simply talking about the DD transition. DD transition, right? So energy gap is too large. As a result, the visible light is not able to excite this electron from the T2G orbital to the EG orbital, right? Okay. Now we have. I think I have almost covered. Right. I will take a couple of minutes before I leave a time for you to, if you have a clarification, you can see the beauty, right? I hope you will appreciate the chemistry, the ligand, the crystal field stuff, the theory, right? You change your
one question.
Modulate your, modulate the ligand. You manipulate the ligand. Pardon?
Sir, am I audible? I had a question.
Yeah, tell me what is the question.
Sir, in case of CO
just hold on. My speaker is giving today. It's a big trouble. Yeah, tell me.
So in case of CO or CN minus, you said that they will be colorless, right?
If one considering only DT transition, I'm not going to the advanced topic. There may be light color will be there. There we need to bring the charge transfer.
Yes, I considered DT transition only.
Yes.
So if the energy difference is too large, then no visible light would be able to excite the electrons from the T2G to EG. So, sir, like in that case, wouldn't that be like white entirely, like predicted to be white at least? So because in that no light should be absorbed because the electrons can't stay in between the EG and T2G levels. That's why I was.
The electron will be in the T2G orbital. If we consider only, there's a hypothetical case where you have your T2G orbital, the electron is there in the T2G orbital itself. There won't be any transition. Yes. Then it cannot be color. The color is basically if we consider only DD transition, the color originates from the transition of an electron from the T2G to the EG orbital. So here there won't be any transition and it should be colorless.
Yes, sir. By colorless means I got it.
Okay. Now look at the beauty. Here you have a cobalt, all are cobalt complex. I manipulate, say for example, I tell that NH3, NO2, NO3, BrNH3, color changes from here to here to here to here, right? Yeah, that's the beauty of your chemistry. You will be able. I have a video, right? Not now, maybe at the end of the classes. I mean, once I finish my topic, I have a couple of videos to show you that how the coordination chemistry, how the color is being modulated by changing your ligands. Okay. Now, whatever I have already mentioned, I have given here. Here I have a fluoride. Energy gap is less, little higher, and then little high, and then very high. So the energy in the visible light is not sufficient to excite this electron to go here. So this fellow, poor guy, helpless guy, is a colorless. Okay, colorless guy. Okay, yeah, that's all. That's all for today. I finished it. The crystal field theory is not over, right? We have many things for today. I could cover whatever that. Now I will give some time. Before that, let me download the attendance list, and then you can unmute your microphone if you have any query in the bonding first part and second part, so that I will be able to I can clarify. We have a bioinorganic, organometallic, and then redox and battery. I hope I will be able to complete, and I hope I am not very fast. Am I very fast in teaching? If you are not able to understand, you tell me. I will explain. Right? Sometime I may pace maybe little fast to cover the topic, but if you are not clear, please let me know.
Sir, one thing, Shushmita has written in the chat that her mic wasn't working, and also she has given her answer in the chat also.
Okay, I did not follow the chats. Right, I am looking at my iPad and the screen. I am looking at. I did not see that. Okay, right. Let me. Oh, she has given the chat.
Yeah.
Okay. Thank you.
Sir, if I don't have any doubt, can I leave, sir?
Yeah. If you don't have a question, you can leave. No problem. Okay. Those who have those who have any query, you can clarify. I'll give 5 minutes time. Sushmita's microphone is not working. Okay.
Sir.
Yeah.
Sir, in case of tetrahedral, the number of ligands is less as compared to an octahedral complex. So why the number of ligands is also less in case of a square planar complex, but the delta value for square planar is more than an octahedral and less for a tetrahedral. Why is that so? I did not understand that.
Yeah. Very interesting, right? You understood the tetrahedral?
No, sir, I am not very sure about the logic of tetrahedral as well for this thing.
No, I mean, I'm not able to get. We see here, right? Octahedral field, what we say that 6 ligands are approaching, right, along the faces. You understood the octahedral field?
Yes, sir. Axial direction is the direction of approach.
It is coming along the faces. Okay, coming along the faces. That one you need to understand. Second one is that the orbital axis, where these orbitals are there located, the position themselves. Your your EG orbitals are along the axis, and the T2G orbitals are in between the axis. Okay. Now, in the case of a tetrahedral, what is happening? The ligands are not coming along the faces, but coming alternate axis. Sorry, alternate corners of the cube. Now you imagine your the metal inside, and then assume your d orbital, all the d orbitals, where it is positioned. Now, where the interaction will be more, where the interaction will be less. Number one. Number two is that total number of ligand is less in the case of tetrahedral with respect to octahedral. As a whole, don't confuse with a square planar. That will come later separately. I will teach you in the Yontel discussion part. I will come to that. In the case of your in a tetrahedral, what we are becoming the alternate corners. As a result, the interaction is completely different from the octahedral. Are you getting my point?
Yes, sir. I got that interaction is different, but still I'm not able to visualize why is it less as compared to octahedral case.
The octahedral case, you have a, say for example, what we have a 6L minus is coming. 6L minus. In the case of tetrahedral, what you have a 4L minus is coming. Assume that you have a Mn plus. Let me put that. What you have? You have Mn plus, and in the case of a 6L minus, in the case of octahedral, and in the case of your tetrahedral 4L minus, you have a 3D. So obviously the interaction here and here is simply based on the electrostatic model. So the interaction here you have a more number of negative or point charge, and here you have a less number of point charge. Definitely your del value should be less. Simply considering the electrostatic model, nothing else. I hope you got it. The reverse, why T2G and EG is going, that is, sorry, T2 and EG is reversing, that is based on your alternate corners. You need to visualize your orbital and your incoming ligands. I hope you got it.
Yes, sir. I got it. Thank you.
Right. Anybody else?